This is part 1 of lecture 2.5, Mathematical Induction. In this video, we will introduce the principle of mathematical induction and learn how to use this to prove statements that hold for an infinite set of consecutive natural numbers. We use the symbol n to denote the set of natural numbers. Depending on the context, this is either the set of all positive integers or the set of all non-negative integers. All axioms of real numbers hold when the set R of real numbers is replaced with the set n of natural numbers, and with the word real number replaced by natural number, except for axiom F6, which is the existence of additive inverses and multiplicative inverses. If we define the set n to be the set of positive integers, axiom F5 for addition, which is the existence of additive identity element, also does not hold. All of these properties of natural numbers can be proved from a different set of initial statements, which are known as the Peano-Dedekind axioms for n. There are 5 of these axioms. These are the first 4, which we shall not discuss as these are not of immediate concern to us. The axiom that is important to our current lesson is the 5th axiom, known as the inductive property of n. It states that if S is a set with a property that 0, respectively 1, is in S, and whenever a natural number is in S, its successor, which is defined in axiom 2 above, is also in S. Then the set S contains the entire set of natural numbers. The second condition is equivalent to the quantified statement for any k in n. If k is in S, then k plus 1 is in S. Take S to be the truth set of some predicate P. Recall that the statement an object X is in the truth set of P is equivalent to the condition P of X is true. Thus, we can restate the inductive property of n as follows. If P is a predicate with a property that P of 0, respectively P of 1, is true, and for any natural number k, P of k implies P of k plus 1, then for any natural number n, P of n is true. This version is known as the principle of mathematical induction. The principle of mathematical induction can be used to prove statements of the form for every natural number n, P of n holds. The proof consists of 2 parts. The first part, called the basis step, is the proof of P of 0, respectively P of 1. The second part, called the inductive step, is the proof of the condition for every natural number k, P of k implies P of k plus 1. In this step, we let k be an arbitrary natural number and assume that P of k holds. The condition P of k is also called the hypothesis of induction, or the induction hypothesis. We need to show P of k plus 1 using the condition P of k. As an example, consider the claim, if a is an odd number, then a raised to n is odd for any positive integer n. This is a conditional sentence with antecedent a is odd, and consequent for any positive integer a raised to n is odd. Let P of n be the predicate a raised to n is odd. We begin by assuming that a is an odd number. Our goal is to show that for any positive integer n, a raised to n is odd. We do this by induction on n. For the basis step, we need to show P of 1, which is the statement a raised to 1 is odd. For the inductive step, let k be an arbitrary positive integer, and assume P of k, which is the statement a raised to k is odd. we need to show p of k plus 1, which is the statement a raised to k plus 1 is odd, using the condition that a raised to k is odd. A useful result is exercise 6 from divisibility, which states that the product of two integers is odd if and only if both factors are odd. We now show the proof. Assume that a is an odd number. Since a raised to 1 is equal to a raised to 1 is odd. This completes the basis step. Let k be an arbitrary positive integer. Assume that a raised to k is odd. Then both a raised to k and a raised to 1 are odd, so the product a raised to k times a raised to 1 is odd. Since a raised to k times a raised to 1 is equal to a raised to k plus 1, it follows that a raised to k plus 1 is odd. This completes the inductive step. Therefore, by the principle of mathematical induction, a raised to n is odd for any positive integer n. This completes the proof. Consider the claim 3 divides n cubed minus n for any positive integer n. Let p of n denote the predicate 3 divides n cubed minus n. We give a proof by induction on n. For the basis step, we need to show p of 1, which is the statement 3 divides 1 cubed minus 1. For the inductive step, let k be an arbitrary positive integer. Assume p of k, which is the statement 3 divides k cubed minus k. We need to show p of k plus 1, which is the statement 3 divides k plus 1 cubed minus k plus 1. We now show the complete proof. When n equals 1, n cubed minus n is equal to 0. Since 0 is equal to 0 times 3, it follows that 3 divides 0. Thus, 3 divides 1 cubed minus 1, which completes the basis step. Let k be an arbitrary positive integer. Assume that 3 divides k cubed minus k. We can show that k plus 1 cubed minus k plus 1 is equal to k cubed minus k plus 3 times k squared minus k plus k. The details are left as an exercise. Clearly, 3 divides 3 times k squared plus k. Also, by the induction hypothesis, 3 divides k cubed minus k. Therefore, 3 divides the sum k cubed minus k plus 3 times k squared plus k. Hence, 3 divides k plus 1 cubed minus k plus 1, which completes the inductive step. Therefore, by the principle of mathematical induction, 3 divides n cubed minus n for any positive integer n. Consider the claim the sum of I squared, I from 1 to n, is equal to n times n plus 1 times 2n plus 1 over 6. In this notation, the number n is interpreted to be an integer greater than or equal to 1, and the sum is equal to 1 squared plus 2 squared plus 3 squared, and so on up to n squared. Also, as n is an arbitrary positive integer, the claim is implicitly asserted for all such n. Let p of n be the predicate. The sum of I squared, I from 1 to n, is equal to n times n plus 1 times 2n plus 1 over 6. We shall prove this by induction on n. For the basis step, we need to show that the statement is true for n equals 1. That is, we need to show that the sum of I squared, I from 1 to 1, is equal to 1 times 1 plus 1 times 2 times 1 plus 1 over 6. For the inductive step, let k be an arbitrary positive integer. Assume that the formula is true for n equals k. That is, assume that the sum of I squared, I from 1 to k, is equal to k times k plus 1 times 2k plus 1 over 6. We need to show that the formula is true for n equals k plus 1. That is, we need to show that the sum of I squared, I from 1 to k plus 1, is equal to k plus 1 times k plus 1 plus 1 times 2 times k plus 1 plus 1 over 6. We now show the proof. The sum of I squared, I from 1 to 1, consists of just one term, namely 1 squared. The expression 1 times 1 plus 1 times 2 times 1 plus 1 over 6 is equal to 1 times 2 times 3 over 6, which is equal to 1. This shows that the formula holds for n equals 1, which completes the basis step. Let k be an arbitrary positive integer and assume that the sum of I squared, I from 1 to k, is equal to k times k plus 1 times 2k plus 1 over 6. Then the sum of I squared, I from 1 to k plus 1, is equal to the sum of I squared, I from 1 to k, plus k plus 1 squared. Applying the induction hypothesis, this is equal to k times k plus 1 times 2k plus 1 over 6 plus k plus 1 squared. It can be shown using algebra that this is equal to k plus 1 times k plus 1 plus 1 times 2 times k plus 1 plus 1 over 6. The details are left as an exercise. This completes the inductive step. Therefore, by the principle of mathematical induction, the sum of I squared, I from 1 to n, is equal to n times n plus 1 times 2n plus 1 over 6 for any positive integer n. You have come to the end of part 1 of lecture 2.5. You may now proceed to part 2. Thank you for your attention.